Okay, good morning. So welcome everyone to next lecture on Introduction to Artificial Intelligence. And today we'll dig into search and some specific structured spaces that we can search through more deeply. And we will cover two topics that were previously each of the topic was a separate lecture. However, the main point of this is that we want to search through the space where we would assume or we would pose additional assumptions to the state space. So we decided to put these two topics together so that we have room for other lectures later in the course, for example, on generative AI and AI safety and so on. So let's dig in. So what we covered so far is that in the second lecture I tried to introduce you and convince you that it's still meaningful and it's helpful for us to have some formal representation of the problem that we are solving. We digged into uninformed search, uniform cost search, breadth first search, depth first search, and so on. And then last week we talked about informed search, A*, and mainly about the heuristics. That heuristic gives us some estimate of the cost from the current state to the goal, and if we have this heuristic informative, it can guide and improve our search because the number of states that we can explore is lower. So this is what we covered so far, and we haven't really assumed anything about what the state is. Right, like we discussed, for example, in the second lecture, we discussed that we can have different formal representation. We can have one formal representation that can be better because, for example, the number of actions is smaller, but the algorithm for generating these actions can be more complicated, or applying these actions so that we can get to a new state that can be more complicated and so on. So we discussed that we can have multiple formal representation, but we have never constrained in any way. It could have been anything if that anything properly represents the problem that we are solving. So today we'll put some assumptions to this structure, like what is the state, and what happens if we restrict these states. Well, something bad can happen and something good can happen. So if we restrict what we can put in the state or how we formalize the problem, so we will say that we cannot really have an arbitrary formal representation, but this formal representation of that one state has to follow some rules. Then of course we will lose generality, because not everything can be captured within one box, right? You can have very complicated situations where you basically are unable to, fill all the rules, whatever the rules are there. So we'll lose generality. However, what we will gain is performance. So if we don't allow, completely arbitrary formal representation in the state, then we can exploit the fact that we will have some assumptions, we will have some rules, some common things that hold for every situation, and we will be able to solve much larger instances of the problem. Moreover, we will not have to come up with our own heuristic for every particular problem. We can, of course, we always can have and most likely should implement the domain-specific heuristic if really this is the problem that we want to solve. However, very often, you don't need to solve really the full scale of the problem, and you just want to solve medium scale problem where any kind of heuristic can be good enough. And for these things, having some more general heuristics that are not always domain specific, that would be very helpful. So this is what we will gain, and this is what we will cover today. So we will have some subclasses of the problems, and generally we are still in the same like realm of problems, so we'll still be in deterministic, fully observable, one agent problem. So like we are not moving away from like the MDPs that we were or where we were. It's just that like we will specify what the state is. So we will start with constraint satisfaction programming, and then like, we'll move to logic and classical domain independent planning. So these two things have basically these aspects in common. Like for all of them, like we'll lose some generality because not everything can be captured as domain independent planning or a CSP. However, if we do represent the problems as a CSP, or if we write our planning problem using some planning language, then like we will gain performance, and we'll not have to come up with the same heuristics over and over again. Okay, so let's dive in, and let's dive into the CSPs. So the CSPs, like what would be the CSP, is that the problem as such is defined by three finite sets. So we'll have set of variables, we'll have set of domains. So for each variable, we would like to assign some value from the domain di to the variable, and then we'll have a set of constraints. And constraint is some tuple on the variables, and basically tells us like what these variables should like fulfill, like what is the constraint. So basically it tells us like what are the allowed assignments for these variables. So a constraint can be that x is greater, or x1 is greater than x2, okay, or that if x1 equals 2, then x2 have to equal 4 or something like that. So like these are the constraints. And this is just a description of the problem, and we will get to examples very, very soon. So I know that this is quite abstract, but basically this is just description of the problem. So this is not state yet, right? Like this is just definition what we want to solve, and or what we are solving, and then a state for the search algorithm. The state would be some partial assignment of values to the variables, right? So like our variables is something that like we have, and we want to find the values for the variables, and some partial assignment of some values to the variables. This is a state. Action in the search problem would be I want to assign some particular value to some particular variable, right? So like, this is my action. And goal state, I want to find such an assignment of values to variables so that all constraints are satisfied, right? So I'm starting in some initial goal state where all the variables are not assigned, so I don't have any assignment at all, and I want to find a path from that initial state to my goal state where everything is assigned and all the constraints are satisfied. So I'm not violating any constraints. So this is a CSP. CSPs are like quite common, even if you haven't met them or read about them. Many problems can be actually represented as a CSP. I would say the most common problem that you can like think of and that you most likely have seen is Sudoku, where I want to like fill in the digits from 1 to 9 into this game plan, where like in each column, each row, and each 3 by 3 box, I need to have all the digits from 1 to 9, so they cannot really repeat. So this is a good example of a CSP, because my variables for this case would be like for each square I have one variable, and for each variable I want to find a value 1, 2, 3, or 9, and so on till 9, and I have constraints, right? Like I cannot have two same digits in a column, in a row, or in this 3 by 3 square within the larger square, right? So like this is one good example of a CSP. Then crypt arithmetic, where like you have some simple equation, and you want to find replacement instead of like letters or variables. You want to find the digits such that the equation actually holds. Graph coloring, like if you have like if you know the like famous problems from theoretical informatics, like graph coloring, like this can be also represented as a CSP. And from the practical perspective, like the most fundamental example of a CSP is scheduling. So you want to like decide which part of the job, for example, to execute in which order and so on. So you have some jobs, some tasks, and you need to assign these tasks, for example, to two machines in time, to allocate the resources for them, such that some constraints are satisfied. For example, that one task, one job cannot start before some other task is completed, right? So like this is an example of a CSP, and specifically in scheduling, like this is like the most useful application of CSP, and there are like many schedulers, many CSP solvers that in practice work and are capable of scaling to very large numbers. Okay, so CSPs are actually very useful and quite used. And for us, like in like this lecture, we will use the like, famous example of the n-queens problem to talk about the CSPs. So, what is the n-queens problem? We will have a chessboard of size n, and we'll use n equals 4, so that we don't have to draw a huge chessboard. So we'll have n times n chessboard, and the goal or the problem is to place n queens on this chessboard such that no two queens attack each other, right? So for those of you who don't play chess, like if I have a queen can move on the column or on the row or diagonally, right? So if I have a queen right here in a chessboard, I cannot place any other queen in here because otherwise they will be attacking each other, right? So the question is whether like I can find such a configuration for this problem so that I can place 4 queens here so that they don't attack each other. So this is n queens problem, and you can see on the slide that this is an example where we can have a solution, and in this case, like this is the configuration where the 4 queens don't attack each other. All right. So as I mentioned, like we are not going to like solve for n queens for larger n's. We are interested how this problem can be represented as a CSP. So what can be the variables, right? Like this is our problem. I want to place 4 queens here. So what can be like the variables? What can be the values? What are the constraints? Yes. So let's start with variables, because you know, like those constraints would have to use those variables, right? So like intuitively you are right, like yes, the queens would not be able to attack each other. However, we need to express those constraints using the variables, right? So like let's start with variables. So as I mentioned, like the CSP, like we want to like restrict ourselves, right? So like specifically, we are looking for such a representation where we will have only variables, and we are looking for some values to these variables, right? So for the n-queen problem, like what can be the variable, right? Because like you're thinking in the right direction, but basically we need somehow to map that thinking into, okay, so variable is this. Yeah. Yeah, go ahead. Yeah. Okay, great. So I will rephrase it. So we can have the variables to be equal to the queens. So basically, one queen can be a variable. So let's say, you know, like first queen would be x1, second queen would be x2, and so on and so on. So the number of variables is n, is the same as number of queens. And then for each variable, I need to define the domain. Like, what are all the possible values that I'm trying to assign to that variable? And your colleague has mentioned two options. Like one option is that the domain would be really coordinates on the chessboard, right? So I can have basically x1, and this can be from tuples 1, 1, 1, 2, 1, 3, and so on till 4, 4 in our case, or an n in a general case, right? So this is possible, right? Like this is my variable, and this is the domain for that variable. Okay? So this is valid CSP. You can write it like this, and then we can get how to represent the constraints and so on. But this is okay. However, like you can see that, like the size of the domain is quite large, and if you recall how we want to represent it and use it, is that we want to start with some partial assignment of the values to variables, and then we can decide and choose, okay, like now I'm going to assign some value to some variable, and I will have number of options, right? I will be choosing which variable to assign to and what value I'm going to assign to this particular variable. And you can see that, okay, I will have 16 options for this one variable, so maybe I can do better. And your colleague already said that, okay, maybe another representation can be that I will not have all the possibilities, but if I knew, or if I knew that the queens can move like by column and by row, so I can say, okay, like I know that these 4 queens have to be in 4 different columns or 4 different rows, right? I know that because like definitely like this would not be a solution. So I don't need to think for the 2 queens about these possibilities, because they will never be true. Like we will always violate the constraints that 2 queens are attacking each other. So I know that it doesn't make sense for us and for the algorithm to search for the combinations that are surely invalid. So what can I do? I can say that, okay, let's assume that I will assign the like column for each queen. So queen 1 would be in the first column, queen 2 will be in the second column, queen 3 would be in the third column, sorry, and queen 4 would be in the 4th column. And now my domain for this variable is only 1, 2, 3, or 4. Because if I assume that my queen1 would be in the first column, what I'm choosing is basically the row, right? And I have significantly reduced the possibilities and the branching factor, so I will not have to look through that huge state space. But generally, this is good, this is a representation for a CSP, but this is also a possible representation of a CSP. It's just that this one is more compact because you wouldn't have to search through irrelevant possibilities. Okay, so we have variables, we have domains, possible values for each variable. Now we have to represent those constraints. So basically, we need somehow to represent that these two queens, or any two queens, are not attacking each other. And let's adopt like this representation so that it's easier. So how can we formally write it down? Right? Like we have already covered that we will not have two queens in one column. So that's fine. So second thing we need to cover is that like no two queens are going to be in the same row. So how can we do that? Exactly. No two numbers are the same, so basically if I have xi is different from xj for all ij and this basically tells me that if I put, for example, queen 1 in row 1, I cannot put queen 2, 3, or 4 into the same row because the values of these variables have to be different. And I need to specify that I doesn't equal to j. Okay, so these are rows, and now we have to cover for the columns. Diagonals, sorry. We have to cover for the diagonals. So how can we do that? Yep. Yes, exactly. So like when you look like what the diagonal means, and like this is a diagonal, but also like this is a diagonal. So basically the difference between column coordinates and row coordinates cannot be the same. Because if they are the same, then basically we are moving along a diagonal. And if you are moving along the diagonal and the values are on the diagonal or the queens are on the diagonal, then they are attacking each other, right? So I have to, like we have to capture this in general. And how can we do that? Well, it's basically the difference between I and j, because like I have like assigned these indices to specific columns. So the difference in these indices cannot be equal to difference in their values, and it's in absolute values because I can go down or up, and these are all diagonals. Okay, so you can see that we had a specific problem, like n-queens problem, and we represented it as a CSP. We defined a set of variables, one variable for each queen. For each variable, we defined a set of possible values, and we are looking for such an assignment of values to the variables, which basically means we are looking for the placement of the queens on the chessboard, such that all the constraints are satisfied, which means that no two queens are attacking each other. Right, so in this way, we have captured the n-queens problem as a CSP. Any questions? So, few more comments to this. So, as we discussed, like our actions is basically assigning some value to a variable, which in this case means that I'm trying to assign and put some queen on the chessboard. And you can notice that there are some differences to the problems that we covered so far. Specifically, we are not really interested in the path to the goal, right? Like when I described that I want to find a configuration where no two queens are attacking each other and they are all placed on a chessboard. I haven't said that, yeah, we are looking in the right way how to put these queens on the chessboard so that they don't attack each other. I'm not that interested in how to put, like whether I need to first put like number 3 and then number 2, like it doesn't really matter. What I'm really interested in is the goal state. Like I described the goal state using some rules and using some constraints, and I want these constraints to be satisfied, but I'm not really interested in like how I get there, right? So this is a small difference from like the previous cases, and it's true only for the CSP. Already in planning, in the second part of the lecture, we'll be very interested in how we get to the goal state, right? So I just want to like emphasize that like this is a small difference, but it's not that important. Formally, basically, this is like what we write down on the board so that you have it also on the slide. What's like interesting is that for many solvers, you know, like when you would need to solve CSP, you don't really need to like implement the solvers for yourself. Again, you can use the existing solvers, and they support some global constraints very often. So, for example, like all different, right? So, like you don't need to specify that every tuple of the variables is like different from each other, but you can say that all these variables like attain different values. So, like there is no two that are the same. And you can like write it down more compactly, but it's basically something that we call a syntactic sugar. So like it doesn't really make the solver more expressive. It's just that much more convenient to write it all different and all variables, and you don't need to specify like for every couple like this this constraint. So these are constraints, and now if we have this representation, how the search works for a CSP. It's good to know like how the search works for the CSP, and we touched on this a little bit when we were like discussing these two representations, right? Because I mentioned that, okay, like yeah, both of these are valid, but this one is better than this one because we have fewer choices. And we'll have smaller branching factor, we'll have smaller like search tree that we need to search through. So it's good to know like how the algorithms work inside, so that you can then choose better representation, and the algorithm that you will use will perform better. And this is not only true for CSPs, like this is true for everything that you will be using. Like the better you understand how the algorithm work inside, and then you have better chance of like choosing the right representation. So let's start drawing how that algorithm would work. So we already mentioned that we'll start with some state that is initial state, and for us, as I mentioned, like the state in a CSP is some partial assignment of values to variables. So if like when we start, we don't have anything assigned to anything. So basically, we don't know like what would be the value for x1, x2, x3, and x4. Basically, I have question marks everywhere because nothing is assigned. So this is my initial state. And we mentioned that one action in this search problem is to assign some value to some variable. So let's say I want to place first queen into first row. So I will, for now, just use like 4 tuples to denote the values, so that I don't have to repeat x1, x2, x3, and so on. So the next state can be 1, question mark, question mark, question mark. Okay, so I assigned value 1 to variable 1. Okay? Then I continue, and I can assign x2, again, value 1. 1, 1, question mark, question mark. So far, so good. Any problem? Any issue with what I'm doing? Yep. Yes, they shouldn't be the same, exactly, because assigning this and getting to this state where I have x equals 1, x1 equals 1 and x2 equals 1 violates this constraint. So in the search procedure, in the search algorithm, whenever I enter some partial state, I can have a check and verification whether my current partial assignment satisfies all the constraints that I have, right? So in this particular case, I know that, okay, like these two values violate my constraints, so I don't have to search any longer. Like, I don't need to look for other variables because I already have a conflict, and whatever is below this search, this node in the search tree is not going to be a solution, because in a solution everything has to like be valid, all the constraints have to be satisfied. So I don't need to look further. I can stop the search here, I can backtrack, and I can assign x2 equals 2. So I'll have 1, 2, question mark, question mark. But again, this violates this constraint, right? Because I placed the queen here. So this is also not going to work. And I again need to backtrack, right? And then I can assign x2 equals 3. So I have 1, 3, question mark, question mark. So I placed my queen here. And this works. This doesn't violate any constraints. So I can continue further and try to assign variable x3 and so on and so on. So this is how the search algorithm works in a CSP. So far, any questions? Basically, the slides summarize what I've said. Okay, so we will like move to a better use of the constraints, because in here in this search, like this is good. This works, but we can do better. Like much better, right? Because in here, like the search wasn't really like all that great, right? Because like, yeah, we were using the constraints, but basically we were using them in a very passive way. Like when you already see, for example, that if I place the queen here and then the second queen here, then basically all these subsequent squares are attacked by either this queen or this queen. Like all these three are attacked by this queen, and this one is attacked by this queen. So like you can already see that like this subtree will not get us to a solution, and we will need to like put this queen to here to get to the solution. But in this search algorithm, we don't know that, because we are just checking whether the partial assignment is violating the constraints or not. And if it's violating, then we stop, but we are not using the constraints in any other way. And we can, and this will give us additional speed up. But before we get there, we need to make some restrictions again, so that we can work with the constraints a little bit better. So what are the restrictions? The main restriction is that the algorithms that are used for CSP usually, in most cases, assume only binary constraints. What does it mean? That the constraints are defined only between two variables. So I don't have variables like x1 plus x2 equals x3, for example. This is ternary, right? I have three variables here. So like most of the algorithms don't allow this. But I want to have like these constraints. So the question is, like, if I restrict only to binary constraints, whether I'm making whether I'm solving, instead of all CSPs, some subset of CSPs, or whether all CSPs can be translated to CSPs only with binary constraints. Right, and like this restriction to only binary constraints is not really like sacrificing anything in terms of expressivity. So, what do you think? Is this a problem? Can we translate any constraint to a binary constraint, or are we focusing only also on subclass? Translate. And can you like see how the translation can work? So if I have such a constraint, how to make from this constraint a binary constraints? Almost. We can say that this whole constraint is a new variable. So I will have new variable x1, 2, 3, and the values or domain for this variable would be those like triplets that satisfy this constraint. So for example, like I will have 2, 2, 4, and 1, 2, 3, and so on and so on. Note that like domains are finite. So yes, I will have to enumerate everything, but yeah, I can do that. So I will create a new variable x1, 2, 3, and then I will have binary constraints saying that x1 has to be the same as the first value in this triplet, x2 has to be the same as this second value, and x3 has to be the same as this value. And I have new variable and only binary constraints between this variable and x1, this variable and x2, and this variable and x3. Okay, so this is a small trick to show you that, like, from now on, we'll focus only on binary constraints, but this is not really like changing anything, and you can still model and represent everything that you would like in a CSP, and this can be translated to binary constraints. So if we have these binary constraints, then we can visualize the dependence and the constraints between the variables as a graph. Like, this is one of the reasons why we did that, and we will have another graph. This is not like graph that we'll be searching, is graph that would help us to work with constraints and use them like more efficiently. So in this new graph, the variables would be the vertices of that graph, and constraints would be edges. So if there is a constraint between two variables, there will be an edge between those two vertices. So this is an example of this constraint graph for the n-queens problem. So basically, you can see that any two variables in this problem are connected via an edge, because there are like all the variables are affecting each other. So there is some constraint between all tuples. For other cases, for other problems, it can be more complicated graph. For example, you can have multiple components, so then basically you know that you can solve them independently, right? So like this helps you to like have another view on the CSP. So now we can like do and use the constraints in some better way. So intuitively, as I was describing, like what we already see when we are putting the queens here is that in this particular case, like we will not have any feasible value for this third variable for x3. So what does that mean, like formally? Formally, that means that we can do something that is called forward checking, and this is basically the same thing as marking x in this chessboard on the squares that are already attacked by some queen. So if I start with placing the first queen in the first row, then I can mark by x all these values from subsequent variables, because all these values are going to like violate some of these constraints. And then, like if I do this and I incorporate it somehow in this search, I would not need to go here and create this new partial assignment and then check, okay, like are the constraints satisfied or not? And I would not need to backtrack and so on. I will basically skip these two attempts and jump directly here, because value 3 would be the first one that is not crossed out. I will put another queen here, and then I will cross out these two and this, and I will immediately know that I can stop searching, because if I have empty possible domain or domain of possible values for some variable, then I know that I cannot satisfy and find a solution, because yeah, I have nothing to assign to variable x3. Okay, so this is forward checking. And like, why we can do that in this representation is because we know like to which variables look if we assigned value 1 to variable x1. Like we didn't know that before. But when we have this representation, we know that, okay, like we assigned value 1 to variable x1, and we need to look for all the other variables that are connected with this variable by some constraint. So that's why this representation is useful, because yeah, I will take this variable, I put value 1 into this variable, and now I'm examining values in all these other variables and crossing out those that are not compatible with this value 1 for variable x1. So basically what I'm doing is I'm forward checking whether, like, what would happen into like domains of the other variables if I assign value 1 to variable x1, and you can see that basically this equals to like crossing out these possible values after placing the first queen here. Okay, any questions? Okay, so now how do we, like we drew it on the board. I said it's sort of hand wavy, so how can we like incorporate it into the search algorithm, and like how to put it more formally down so that like you can actually implement it. So whenever the search algorithm assigns some value to some variable, the algorithm can check all the constraints and examine all the other variables xj and evaluate whether the values in the domain of those other variables are satisfying the constraint Cij. And if they are not, they can be removed from those domains dj, and we'll keep them only we keep only those that can satisfy the constraint. So how can we like integrate forward checking, where whenever we decide and make some assignment, like this assignment can then be followed up by this procedure that we can like call in a function as a forward checking, and basically like we will examine whether like how the changes would be reflected in domains of all the other values, right? So like whenever we make this assignment, like we can perform the forward checking call, and if there is still some valid assignment, meaning we haven't emptied any domain, then we can continue. So for this, we need to, of course, like keep these domains some sort of copies, because we will be like removing and adding back to these domains as the algorithm will like search through all the possibilities. And as I mentioned, like if we empty some domain, then basically we can immediately backtrack. And already this gives you like one first domain independent heuristic that you can always use in a CSP, and it's a very good thing. And this is called the minimal remaining value heuristic. Because, you know, like when we discussed that, yeah, like we start with some partial assignment, then we select some variable, we will add some value to that variable, and we continue further. This is the search. But we haven't really specified which variable to choose. Why I started with x1. Like there is no strict rule that I have to start with x1. I can choose any variable I want. And one good heuristic is to start with such a variable that has the lowest number of possible values, because this is like the most constrained variable. When you are planning with someone, for example, a trip, or when you are planning a meeting with your advisor, or you will be planning meeting with your boss, starting with person that is the most constrained is the easiest one, because yeah, like you all can find a good time to meet. That can be Tuesday 9, Tuesday 10, Tuesday 11, and so on and so on. And all these are good for you, but for them, there can be only one possibility, Tuesday at 7 p.m. Right? And like you don't have to try all these attempts. You can just ask them when they have time, and that would be the time of the meeting, right? So this is the same thing. Basically, you can start with the most constrained variable because you don't have that many options. So you will, you know, start with that, and that way, like the search tree would be much, you know, smaller, because you will have smaller branching factor here. So like you will not have to explore some part of the search space that are again irrelevant, right? So like you will not need to like find and negotiate the combinations between the variables that are less constrained, and you will start with the most constrained variable. So this is a first like example of a domain independent heuristic that like can significantly speed up search in a CSP, because you know like this really works for any problem. So like it's not example of a heuristic that it's a Manhattan distance in a maze, because that works only in a maze. This is a heuristic that works for all CSPs. Okay, any questions? I'm rushing today a little bit because like we have, you know, 2 lectures in one, sort of. I removed some things, but still like there is quite a lot of content. So feel free to stop me if something is not clear. Okay, so how would that like pseudocode with search like look like? Basically, as we described, like whenever we make some assignment to some variable, and I can choose that variable according to the MRV heuristic, but like there are other heuristics that you can choose and you can like find out. So like this is just one example. So after we choose some variable, we can choose values for that variable, and after making this assignment, I can run the forward checking algorithm, and if like there is still a hope for having a solution, then I can continue with the search. If there is none, I can backtrack. Right, so like that, this is quite simple. So this is already much better than just using the constraints passively, because I can, you know, like prune out a significant part of the search space, and you know, like in this case again, like this is easy so that we can fit everything on the board and on the slide and so on. But again, like imagine that it's not that clear that the solution will not exist, and between here and like these two variables that are basically like causing the fact that like there is no solution here, you can have many other variables that you will try to assign, and you will like try these assignments multiple times before figuring out that like, basically this doesn't work. And for these cases, the forward checking will already speed the search significantly up, because you will not do these repeated searches. So this is good. However, it can be better. It can be still improved. And the main thing is that if we remove, you know, some of these values based on the constraint, then we can violate some other constraints, right? Like basically what we are doing is that, you know, like we are crossing out some of the options, and if I again backtrack in my example here, and I do this again after like this first assignment, then you know, like you can already see that, you know, like placing queen here is not good, because like it will, you know, violate here, and if I place it here, it's not really better, because as I'm like limiting the number of possibilities for other variables, I'm also like limiting and like implying what other can happen in the problem. So maybe I don't need to, you know, like do this sort of one pass, right? This forward checking is really like making a one pass for this variable and this assignment with all these other variables. Because what I did is that, okay, like I took this variable and this assignment, and I made sure that all these other variables have only those values that like can satisfy the constraints given this assignment. However, like it's not clear whether there is some possible assignment in here, whether these other values in these other variables are like whether they are satisfiable. So we can do a little bit better, and we can check not only these constraints between this variable and all the others, but basically for all the variables, right? So in a nutshell, whenever we make some domain of some variable smaller, so we cross something out, we will check whether in other variables there are still values that can satisfy the constraints. And we can do this like repeatedly until we don't cross anything out. So we will not do this just once, but we'll do that till we are until we are crossing some values from some domains out. And when we don't cross anything out, then we stop, right? So basically this is like forward checking plus plus. However, the algorithm that I have just like described in a high level is called AC3 algorithm, and we will briefly go over it. So why AC3? It's because it's called based on making the edges or the arcs that correspond to constraints consistent. So it's like arc consistency, and arcs or edges are corresponding to the constraints. So how do we do that? Well, basically, the arc consistency is like the forward checking between like all possible constraints. So forward checking really did the fact that it made like this constraint consistent, this constraint consistent, and this constraint consistent, right? So it removed the values that were violating these constraints for like these tuples of variables. And in general, this is what the consistency for those constraints or for those edges mean. So we are like having some flags so that we know whether we removed something or not. And for each value in variable for a variable x, y, so this is domain di that is assigned to variable xy. We are checking like whether there exists some other value in the domain dj such that like this constraint is satisfied. And if it is, then yeah, we can keep this. If it's not, we can delete it. And if we delete it, then like we are making this this domain smaller. And if we are making this domain smaller, we return true for this arc consistency method. And in AC3, what we are doing is having a queue of all the constraints that we need to check and we need to make consistent. And while this queue is not empty, we are still checking the constraints that are in this queue, making them consistent. And if we have deleted something while making this particular constraint consistent, we add all the other variables and all the other constraints that are linked to this particular variable, and we need to recheck it again and again and again. So this is the AC3 algorithm. It's very good and very powerful. Like, we'll not have time to like go over this algorithm step by step, but it's not really like that complicated. Like when you basically examine and like fully grasp like the idea of making one edge or one constraint consistent, then basically this is just repeating this over and over again till everything is consistent, or basically there exists some chance for a solution. Will this algorithm stop? Like, this is a fair question because we have a while loop over some queue where we are constantly pushing something into. So, whenever you see something like this, you should be cautious whether such a while loop where you constantly push something into this queue, whether you will stop or not, or run forever. So will this algorithm ever stop? Or it can run forever? What do you think? Sort of by common sense, you should get to the answer that it will stop, because I won't be telling you about algorithm that can potentially run forever. Right, so like a common sense answer, is most likely it will stop. But there is a better answer why it will stop. So when we are adding to the queue, we are adding to the queue, so we are basically expanding and prolonging the loop. If we make some deletion in variable a while making the constraint AB, so between two variables, consistent. So recall that, you know, in here we return true in case like we are deleting something from variable or from domain di for variable xi. So whenever we delete something, this method is true, and we add new variables and new constraints into this queue. However, since we have finite domains, right, we cannot delete forever. We can delete at most number of variables multiplied by size of their domains, and that's it. Like we cannot be deleting forever. Then we will have empty domains, and the algorithm will basically stop. So yeah, the algorithm is complete, and it will eventually stop. So this is AC3. It will significantly reduce the domains and the search space. So, for example, for cases like Sudoku, like without AC3, it would really take a long time to solve Sudoku, right? But with AC3, if it's implemented correctly, then like you can have Sudoku like solved within a fraction of a second. Despite the fact that it's really a huge state space, right? Like you have 9 times 9 variables, and you're looking for like assignment of values to those variables. So like if you create a search tree out of Sudoku, it's really a lot of states. However, with CSP, with AC3, you can really solve it under a second. So this is AC3. Unfortunately, like AC3 is not really like the solution. Like AC3 is really just making the constraints consistent. So there is a chance there is a solution, but it doesn't guarantee you a solution. And a simple counterexample is this one. Like you have 3 variables. Each variable has 2 possible values, 1 or 2. And all these variables have to be different from each other, right? Whenever the algorithm examines every constraint, it's possible to satisfy it. Because if I look at x1 and x2, yeah, I have different values. If I choose 1 here, I can choose 2 here. If I choose 2 here, I can choose 1 here. Awesome. Like this is satisfiable. The same for this constraint, the same for this constraint. The problem is that like all 3 together, we cannot really satisfy. So the AC3, similarly to forward checking, it's a method that will prune out the search space significantly. And like without that, you will wait for a very, very long time. So it's really helpful, but it's not really the solution. Like you still need to combine AC3 with search, because in cases like this, AC3 will fail you, right? So you still need to say, okay, so now I'm going to search. I'm going to assign value x1, value 1 to variable x1, and then you will find out, oh, but it doesn't work. Then you will try 2, then you will find, yeah, this doesn't work. So then you can say that it doesn't have a solution. Okay, so AC3, the minimal remaining values. So these are like some tricks that you can use and implement in CSPs to speed up the process and to basically allow you to solve much, much larger problems, right? So like if you implement Sudoku without this, as I mentioned, like you will wait for hours at best, for years at worst. So really like using this assumption that I don't have an arbitrary state representation, but I have some specific state representation, allows us to solve much, much larger problems. Besides like AC3 and MRV heuristic, there are many, many other tricks that are implemented in CSP because CSPs are being solved since 1960, 1970, right? So like over 50 years of people knowledge and tricks are implemented into those solvers. For example, like you can have backjumping and dynamic backtracking. Like in a search tree, in a standard search, when you are backtracking, you are going one level up. In CSP, thanks to this specific structure, you don't have to. You can jump to the reason why you are unable to satisfy some constraint, because you know, like, this is the problem, this is the constraint that I'm unable to satisfy, and unless I fix this variable, I don't need to search for anything else. So the search can be much smarter and jump from here to 7 levels up, and again, you will gain a significant speed up because you're not searching through irrelevant state space, right? So these are all the examples on a, like very quickly that like show that like this restriction to some specific representation can give you again like a huge leap forward in terms of scalability. Okay, any questions to CSP? Like, this is, really 60 years of interesting and rich topic, so it's not the main point here to explain everything about CSPs. If you're interested, there is basically a whole semester course on Charles University just on CSPs. There are many books on CSPs, so there are many solvers with CSPs. So really, it's really just for you to understand that if we like restrict ourselves, we can gain a lot, while paying for the fact that, okay, like not everything can be represented as a CSP. So, any questions to CSPs? Okay, so let's move to logic and planning in the remaining part of the lecture. And as I mentioned, like the CSP can be restrictive. Like the example that we can use here is this famous example with monkey and banana, where there is a room where we have a monkey, we have a box, and there is a banana on the ceiling. And what the monkey needs to do is to figure out that, okay, it needs to move the box into this middle position, climb on top of the box, so that it can reach the banana. It will be very difficult to represent this as a CSP, because yeah, like you will start, okay, I can have a monkey. Monkey can be on 3 different positions, and then on the box or on the ground. But I need somehow to get that box to the middle position. So it's not really convenient. Like the CSP can really, for some cases, be too restrictive. So what can be more general representation? Well, one formalism that can really represent many things, and in, again, 1960s, 70s, people thought that this is like the formal representation that they will use for basically everything, is logic. And one example of logic is first order logic, or what we can use on what had been used before for representing knowledge is, for example, situation calculus. So what we can have and how we can describe situations like this. So basically, again, like what we are like restricting ourselves is how do we do formalization? How do we like formulate states and actions? And we can use logic for this purpose. So for the states, we can basically have world state histories. So we already had that, for example, with chess and so on. So basically from some initial situation, everything that happened, this is my description of the state. So yeah, this is like something that you are already familiar with. And then we can have predicates describing what is the like what is true and what is not true. And these predicates can be either rigid, so they are true forever, or they can be changing because they are true in some situations and they are not true in some other situations. So the predicates that don't change their values are called rigid. The predicates that change their values are called fluents. And the examples of a fluent can be that monkey is, for example, at the banana right now. Now is some description of the situation. Rigid predicates is that like monkey walks. And monkey walks for the whole duration of the problem. So this is like one way how can we describe the situation, and like this is what we can use for the formalism. And when we want to like create a new situation, the new situation is, and the state is basically result of making some action in some state, right? So again, like we are not moving to, like away from MDPs. It's just that we are using a different way how to describe it, and basically like the result of action A executed in state S is a new situation, is a new state, right? So like, we just don't describe it in any other way. In situation calculus, it's described this way. So to give you an example, if I'm in initial situation, like this is my description of the initial situation. The monkey is on the right, it's on the ground, the object is on the left, and like nothing is on top of the object. And if the monkey walks, then like it can be next to the object if or the box, sorry. And if the monkey then climbs on top of the box, then the monkey is on the box. And you can see that basically the states are like our history of all the actions that have been executed, right? So like this result of init walk basically represents whatever changed from the initial situation, and this is our description of the state. So when we have this description, the actions are basically axioms in logic. So we can have like these axiom rules how the situation and things change in the world. So for example, for walking, like for all agents walking from one spot to another, the agent has to be capable of walking, so we cannot really do the action walk for the box. And the agent has to be on the ground in the situation where we want to execute the action walking. And if it's true, then we can resolve that agent is still on the ground, it's in this new position, and our like state changed by basically applying this action walk. So like the history has been extended by one action walk for this agent, right? And like this can be instantiated for other constants if we have, for example, multiple monkeys and so on. Similarly for climbing, right? Like we have some preconditions that have to be like satisfied, and like we'll have some other facts that will be true, some predicates will be true after like the monkey climbs on top of the box. So in this way, basically we can define the states, the actions, and when we have this definition, then we can like say that okay, now when I want to solve the problem, like where is the search in all of this? It's basically okay, I want to find such a situation where the monkey is in the middle on the box, so that the monkey can grab the banana. And I'm looking for such a situation Z, and I'm checking whether it's true in our world with our axioms and our predicates that I can prove this, right? And if I can prove it, if I can show that this is actually true, then I will find a plan, because my Z, my situation, is really like concatenation of all the actions and their results. So this would be my plan, right? So again, this is to demonstrate that we can use logic for searching, and proving something in logic is search, right? Very, very briefly and on very high level, but these two things are very closely related. So this is like small introduction to like how different representations we can have and we can use. And logic is fine. It's basically really like you can express quite a lot of things using first order logic, and there are more complicated variants of logic. You can have model logic, where you can have model operators telling you that like there is that eventually something will become true, so there is a time element. You can have other operators telling you that other agents know something, that you can specifically, for example, express common knowledge. So if you have multiple agents, you can express that all the agents actually know that something is true, and so on. So like you can really have like very strong logic representation of the knowledge. However, even for this simple logic, like the scalability is quite limited. So like one of the things that we wanted to achieve was to have some representation that will allow us to solve larger problems. And this is not really like the case. So what is like the case, and is there some formal representation that would really be like the right formal representation for large scale domain independent problem solving that fits into MDP, or the space where we were so far? So single agent, deterministic, and we are looking for like going from here to goal state as quickly as possible. And yes, there is, and this is called domain independent or classical planning. Right, so again, on masters, you have a whole course on just planning, because this is a introduction to AI. And really, this topic of planning we will cover in 15 minutes, and it's worth a course, because really there are many things, right? So we're unable to show you and to explain everything, but it's really like the right representation for like describing these problems in a domain-independent way, such that you are able to solve larger problems, and you don't have to like re-implement the search again and the heuristics again, and so on and so on. So you can actually use it. So like many of these following slides are based on slides by Karmel Domschlag or Antonín Komenda that were like teaching the planning before. So the like coloring is a little bit different, but otherwise everything holds. So for the planning problems, like this is what we want to solve. Like as we started with, like two lectures ago, we want to find the plan, the sequence of actions from the current position, from the current state to the goal state, and usually we want to find this sequence of actions as quickly as possible or as cheaply as possible. We want to find the optimal plan if we have some costs, and so on and so on. So how can we have a good representation for the states? So we want to, and we are looking for some language that would like help us to like reduce some redundancy, if there is some redundancy in the problem. Not everywhere there is some redundancy, but for example, if there are some symmetries, or if there are some things that don't change and we need to copy it again and again, like this is something that we want to avoid, and like planning language is language that can simplify this. Basically, the world state would be represented using some state variables, and that can be true or false in some other languages, and the valuation of these state variables is a state. This is similar to CSP. However, in CSP, like we were looking for some assignment. In here, like we can have different values to these variables, and it can change because like the problem would be more rich than in a CSP. And the main point is like two things: to have some like conscience representation of the problem, and to be able to like have much faster computation, so that the problem structure can be exploited much easier and in more general way. So like we don't have to specify the domain specific problem like heuristics all the time. So the main language that we will cover and that we will use is strips. It's not the only language. Like the most common language is PDDL, but strips is simpler and it's sufficient for us. So what is strips? Is the language for describing the planning problems. And we have a tuple PAIG, where P is a finite set of states, and basically, like these are the atoms that represent the states, and we have some finite set of these atoms, and each atom is some Boolean variable. Initial state is I, so basically this is some subset of these atoms that are true in the initial state, and the goal state is another subset of these atoms, and we want them to be true in the goal state. And then the set of actions is again finite, and each action is specified with some precondition and some effects. Preconditions are again subset of atoms that have to be true so that we can apply that action. And the effect can be twofold. We can either add some atoms to be true if we execute that action, and we have negative effects. So these delete atoms are those atoms that will not or stop be true after we execute this action. Right. So, for example, I can have atom that I'm placed here in these coordinates, and if I move forward, then one new atom will be true because, like, I'm now here in these new coordinates, and the previous atom that I was here is no longer true. So I have added something, and I have removed something. Okay. So, as I mentioned, like the strips is like fairly simple. And like it's easy to think about the problems in strips. At the same time, it's like fully expressive, so we are not really like losing anything. So like formulating the problems in strips is like good enough, and other languages offer again some syntactic sugar to express some of the issues more compactly. But basically, you can also represent it in strips. So to give you another or good example of how we can represent problems in strips, in these slides like we have an example of a Sokoban. Do you know Sokoban? Yes? Who does know Sokoban? One? Two? Okay. So in Sokoban, you have an agent, like this is you, this is the agent, and the goal is to put all these boxes to some to these marked squares. However, the agent can only push the box. It can never pull the box. So you have to be careful where to move and which boxes to push, because if you start, for example, by pushing this box to the right, you are done, because you will never ever get that box like from this wall unless you will create a space here and you can like push it all the way down, right? So you can only push the boxes, and you can only push those boxes like that are like single boxes. So you cannot push two boxes at the same time, right? So like there has to be a free space when you are pushing a box somewhere. So this is an interesting like example for domain-independent planning, because it's not that easy. Like if you will download Sokoban, I'm pretty sure there are like some clones of that game. You can download it and play it on your cell phone. Like it's quite fun and challenging, because like finding the right plan is not always that easy. And of course, like if you advanced to more and more complicated levels, it's a nice puzzle, right? So feel free to download it and play if you don't know the game. And it's also not that easy for the algorithms, right? Because even though that it's a fully observable problem, we can see everything. it's deterministic, there is no stochasticity. Still, you need to be careful, like what to execute first and how to plan carefully the actions in this environment, because like if you push some box in a wrong direction, then like this can lead you to a failure, right? So like there can be really very specific particular sequence of actions that you're looking for. Like they can be, for example, one sequence of actions in a state space that is really, really huge. So you have 10 power to 10 states, and in this huge tree of 10 power to 10 states, you're looking for one path. So that's really difficult, right? Like this is a huge tree and you're looking for one path. So that's why like this is a nice example, and like showing why planning is difficult despite the fact that it's basically the easiest case that we are covering here. So how can we describe it? Well, we can have possible positions, right? So like we can have some coordinates of this map, and we can have like description, like which like places are adjacent to each other, where are the boxes, where are the like target squares, and so on and so on. And then we can have operators that are basically the actions, and as we specified before, like we can have preconditions. So if we are moving, for example, the agent moves from position X to Y, then of course the agent has to be at position X, and the position Y has to be free, and they like these two squares have to be adjacent to each other so that we can actually move from X to Y. And then at effect is like the player would be at position Y, and the delete effect would be that the player is no longer at position X. So like these are like this is the way how we can in general caption the actions in strips. However, like the strips really uses not these general descriptions, like this is what you can write, but what is really used for planning are these like grounded actions, where basically like the specific constants are replacing like those variables that you specified here, right? So like this is something that you don't have to do. This is exactly what the planner does for you. But it's good to know that, yeah, like this is the space that we are really searching through, right? Like not this one. This is more abstract, more compact representation. So we can have this representation of Sokoban, and if we have like super simple example like here, then the goal state is that okay, we want to specify that box, some box, we don't care which one, but some box is here and some other box is here, right? We don't care where the player is, we don't care where other things are. If we do, we need to specify it in the description of the goal state. So now we have this description of states, we have description of actions. So can we just use A star as before? Like what's new here? Well, we can, and basically A star is the most used planning algorithm. The trick is that you don't have to specify those heuristics, because when you write down the problem using strips or PDDL, like you can use domain independent heuristics that are again already baked in and implemented in the planners. So recall that like last week we have discussed that okay, basically like a good heuristic for a problem is to solve a relaxed version of the problem. And then we specified okay, for playing a maze, a relaxed version of the problem is that we assume there are no walls. For 8 puzzle problem, we assume that we can just move all the tiles directly to their correct squares. And we had Manhattan distance as the heuristic. And yeah, like the idea was the same, right? Like we wanted to use a relaxed version of the problem, the simpler version of the problem, solve that, and use that as a heuristic. But like when you want to implement it in A star, you really need to implement it for your particular domain. If you have it as like in strips, then like these are already implemented, and there are many other heuristics that you can and you have implemented in the like planners. So for example, you can have like abstraction. You can have solve smaller problem. You can solve like independent subproblems. You can have landmarks where you can identify some sort of key points that you know that, okay, I surely need to accomplish this. So you can, again, split the problem into subproblems. And the relaxation is, again, like one of the most common examples of a heuristic. And it basically means that we want to solve a simpler problem. So in planning, how can we create this in a domain-independent way? Well, basically, we will like use and we will ignore the sort of bad effects of actions. And what is the bad effect of action? Well, it's basically removing something that was true before. So these are the delete actions. So if we ignore them, we can have a relaxed or sort of plus version of the problem. And yeah, basically we can, like, instead of having planning problem P, we can have planning problem P plus, where everything is the same and all the actions are the same, but we remove the delete effects, right? So this is the only change that we will do. And in Sokoban, what that means is basically that we will start exploring everything at once. So we'll start at some position, and if we move left, then we have basically our agent on both places, like where the agent was before and in this new place. If we move right, then again, like everything is true, right? So basically, what we are doing is that we are making everything true and reachable what's possible, right? So this is the relaxed version. And if we find an optimal solution in this relaxed problem, we will have heuristic H plus. This is the solution, the optimal solution of this relaxed problem, and this is a heuristic to the original problem, and it's admissible heuristic. However, like finding this is still NP hard, so we can do something simpler, which is H max heuristic, and this is the last thing that I will cover. To compute the H max heuristic, you need to compute something that is called reachability graph. So basically, we want to really to mark everything that is reachable or possible after making some action, then something else becomes true, and we can then make new actions, and then new atoms will become true, and so on and so on. And we want to terminate this whenever we'll find out that, okay, like everything that was supposed to be true in a goal state is already true, like we have satisfied it. So this is one example. Basically, what we want to like get is that all these C, D, E, F, G atoms would be true. So we start with A equals true, like from the beginning. We can like perform only action A1, but then A, B, C is true, right? Then we can perform other actions, also A2, A3, A4, because like these preconditions are satisfied. So then we can like execute more actions, and then we can execute more actions A5, A6, and these A5, A6 like give us the additional atoms that need to be true in order for us to be able to reach the goal. And if we have all this, then like we are able to reach the goal. So this is the relaxed planning graph, and basically again, like this is the simplification. Like I assume that nothing will be deleted, so I assume only things will be added, and this is the sort of happy case scenario. How can I get to the goal state? So how can I use this to compute the heuristic that will help me in the original problem? Well, I can compute like this number of minimal actions that I need to have in order to reach the goal, and I will do that using using this relaxed graph. So basically, I will start with 0 here, and whenever I have action, I will take the maximum of all the like values that I have in preconditions and increase it by 1. if I have some atom, then basically whichever like minimal value I was able to reach that atom or to make that atom true, like that is the value of that atom. So I start with 0, and then like the value of that action is 1, and I have 1 here because I need to make at least one action to make these two atoms true. Then if I like continue, then of course like making this action like requires these two things, these two atoms to be true. So it's 1 plus 1, it's 2. So I have 2's here, and so on. So I will get to all of this, and basically you can see that like all these values are necessary, and all these like atoms are necessary to be true for us to be in the goal state. And I need to do at least 3 actions to make the goal state true, because I need at least 3 actions to get to G being true. Okay. So this is the HMAC heuristic, and again, like this is a heuristic that you have already implemented. You don't have to do anything, and you can use it in the planning problem. So that's it. I apologize for being a little over the time, and this basically concludes the single agent deterministic planning problems and problem solving. And next up, you will dive into reinforcement learning, and then we'll move to games and to uncertainty and all these other more complicated things. Thank you very much.